Welcome to all. First we define an analytic function at a point A. The function f is said to be analytic at a point A if it is differentiable in the neighborhood of A at every point. At every point in the neighborhood of A, the function f is differentiable. Then f is called an analytic function. Here first we define a singularity. A point A is called a singular point or a singularity of f of z. The function f is not analytic at a point A. At every point, analytic at some point of every disk z minus a equal less than r. That is, the function is not analytic only at a point at the A. Example: find the singular points of f of z equal to 1 by z and f of z equal to 1 by z into z minus I. So now f of z equal to 1 by z, then 1 by z, here z equal to 0 is not an analytic. Since suppose if z equal to 0, then f dash of z equal to 1 by z square, that is tends to infinity. Therefore f of z is not analytic at z equal to 0, which imply f of z is analytic except at z equal to 0, which imply z equal to 0 is a singular point of f of z. And another example, here clearly f of z is not analytic at z equal to 0 and z equal to I. Therefore z equal to 0 and I are the singular points of f of z. Here isolated singularity now. So now a point A is called an isolated singularity if f of z is not analytic only at a point z equal to 0 and is analytic every point of the neighborhood z minus a less than r. So for example, here f of z equal to z plus I by z square into z square plus 1 has three isolated singularities. That is, a denominator value, when the denominator value becomes 0, then the point is called a singular point. That is, z equal to 0 is a singular point and z square plus 1 equal to 0, which implies z square equal to minus 1, that is z equal to plus or minus I. Therefore the function f of z has three isolated singularities, namely z equal to 0, I and minus I. So classification of the isolated singularities. The point A is called an isolated singularity of f of z or be a r greater than 0 such that f of z is analytic and in the modulus z minus a is less than r. In this domain f of z can be written as the Lorentz series expansion. Then f of z equal to here an and bn is denoted by the Lorentz series expansion. That series summation bn by z minus a power n is called the principal part or singular part of f of z at z equal to 0. So this singular part, that is the denominator value z minus a power n. Z minus a power n, the denominator is a singular part or principal part f of z at z minus a. That is, z minus a power n is involved in that series. So there are three types of singularities. One is removable singularity and pole and essential singularity. First we define a removable singularity of a function f of z. So the point A is called a removable singularity if the principal part, that is z equal to summation n equal to 1 to infinity bn by z minus a power n has no terms. That is, the denominator value does not involve in the series. Then the point is z equal to 0 is a removable singularity. For example, find the removable singularities and classify the singularities. First one is sin z by z and the second one is z minus sin z by z cube. Suppose f of z equal to sin z by z, then the singular point, isolated singularity is z equal to denominator value z equal to 0, then it becomes infinity. Therefore z equal to 0 is an isolated singular point. Now sin z by z equal to 1 by z into z sin z expansion z minus z cube by 3 factorial z by 5 factorial etc. So z becomes outside and z cancel. So remaining values are 1 minus z cube square by 3 factorial and plus etc. So therefore the principal part, there is no principal part, which imply The singularity is a removable singularity. So by defining f of 0 equal to 1, the function becomes analytic at z equal to 0. And the second example, f of z equal to z minus sin z by z cube. Clearly 0 is the isolated singularity. So z equal to 0, the function f of z tends to z infinity, which implies z equal to 0 is an isolated singularity. And the expansion is z minus sin z by z cube. So z into sin z expansion z minus z cube by 3 factorial. So z cancelled, and the remaining value is z cube by 3 factorial minus z power 5 by 5 factorial plus etc. And z cube, the denominator value and the numerator value becomes cancelled, and the remaining values are 1 by 3 factorial minus z square by 5 factorial plus z power 4 by 7 factorial minus etc. Which imply the principal part, there is no principal part, which implies z equal to 0 is a removable singularity. Suppose if f of 0 equal to 1 by 6, therefore the function becomes analytic at z equal to 0. And second one is a is a isolated singularity. The point A is called a pole if the principal part has a finite number of terms at z equal to a. That is b1 by z minus a, b2 by z minus a square up to etc. br by z minus a power r, br not equal to 0, which is the finite number of terms. Therefore the point z equal to a is a pole of order r, that is power z minus a power r. Then z equal to a is a pole of order r for f of z. If a pole of order 1 is called a simple pole and a pole of order 2 is called a double pole. That is, suppose if b1 by a z minus a term only involves, then a is a simple pole. If b2 by z minus a square is also involved in the series, then z equal to a is a double pole. For example, determine and classify the singular points e power z by z etc. So first define function f of z equal to e power z by z. The expansion of e power z is 1 plus z by 1 factorial plus z square by 2 factorial plus up to etc. And expansion values 1 by z plus 1 plus z square z by 2 factorial plus etc. So therefore there is no cancelling 1 by z, which implies z equal to 0 is a principal part. Z equal to 0 has a principal part, only one term, as a single term. So therefore z equal to 0 is a simple pole for the function f of z. The function f of z equal to tan z becomes sin z by tan z expansion sin z by cos z. So when the cos z becomes 0, the function, the cos z values are 0, involves only cos pi by 2, cos 3 pi by 2 plus etc. So therefore the singularity of f of z are pi by 2 plus n pi, where n belongs to z. All the singularities are the simple poles, that is pole of order 1. And the third one is f of z equal to cos z by z square. Again cos z expansion 1 plus z square by 2 factorial z power 4 by 4 factorial minus etc. So expand bracket removing 1 by z square plus minus 1 by 2 factorial plus z square by 4 factorial minus z power 5 by 4 6 factorial plus etc. So therefore the terms involves 1 by z square, which imply f of z has a pole of order 2. Z equal to 0 is a double pole. And the third one is fourth one, z square plus minus 2z plus 3 by z minus 2. Here the function z minus 2 power z square minus 2z plus 3, the division z minus 2 division z square plus 2z. So z is z square minus 2z, the remaining terms 3. So therefore this division becomes z plus 3 by z minus 2, which imply all the terms involving only z minus 2. So therefore z expanding 2 plus z minus 2 plus 3 by z minus 2, which imply the function values involving 2 into z minus 2 power 0 plus z minus 2 power 1 plus 3 by z minus 2 power 1. So the pole becomes the denominator value z minus 2 power 1, which imply f of z is f of z has a simple pole at z equal to 2. So therefore the function f of z has a simple pole at z equal to 2.